So, okay, so then let's do this. So first, and I'm going to be a little bit, we'll give it. So I want to look at V epsilon times U epsilon minus V epsilon, where V epsilon is the Biot-Savart kernel applied to this omega. What did I call it? Unfortunately, I changed the notation, but it's mu sub gamma comma epsilon, the Biot-Savart kernel applied to this modification of the measure living on the curve gamma. Okay, and what this is, remember, is the curl of minus Laplace inverse of eta epsilon convolved with mu gamma. Let's call this the curl of psi epsilon. So that's, I'll call that psi epsilon. Okay, and so, again, we know sort of everything about this, at least away from the, we can compute pretty well if we want to. And so here I'm going to, so let's say we can check, so we can easily compute the behavior of, say, psi epsilon and V epsilon as x goes to infinity. And what do we find? We find, I believe, e.g. psi epsilon behaves like 1 over x squared. So, so what am I doing here? For psi epsilon, I have this curve, and I'm convolving with the Green's kernel with the Green's function R3. The Green's function R3 behaves like 1 over x, and so if I'm far away, I'm integrating this kernel who behaves like 1 over x against something that's supported in some Hammett region. And so the decay should be at least 1 over x. But in fact, because the integral of this thing is 0, you get an extra order of decay. So we've done things like this before. And then the v will decay, I guess, faster. It'll decay like 1 over x cubed. Okay, and so we can, so what do we have? Okay, and the point is, because this decay of psi, I can justify integration by parts and move the derivative onto u epsilon minus v epsilon. And I like this because I don't have control over u minus v, but I do have this nice estimate for the curl of u minus v. And what we know is that this is, so we know that this is small in exactly, well, let me write it like this. We know that the homogeneous flat norm of this curl is small. And what's the homogeneous flat norm? The homogeneous flat norm is exactly what we get if I let this thing, so this is of order epsilon in the homogeneous flat norm. And that means that if I let it act on a test function psi, whose curl is bounded by 1, then I get a small result. And so by the definition of the homogeneous flat norm, this is bounded by exactly the curl of psi epsilon L infinity times this homogeneous flat norm of u epsilon minus v epsilon. Okay, and and this is of order epsilon. And what is this? Well, this is just v epsilon L infinity, because that's what the curl, so that's what v is, right? And so and that we know from up here. That's, I guess we said that's of order 1 over epsilon. So this is order 1. And remember, we're eventually going to divide by log epsilon. So when we divide by log epsilon, order 1 becomes order 1 over epsilon. We let epsilon go to 0, it vanishes. Okay, so so that's the first estimate. And we use the definition of the homogeneous flat norm in an interesting way, moderately interesting. Okay, the second estimate is now easy. It's pretty easy. So let's see if I can get this right. So this is okay. And so on the left-hand side, I have u squared minus 2uv plus v squared. On the right-hand side, I have u squared. There's a minus 2uv here in the last term, and then there's a minus v squared plus 2v squared. Okay, equal. And this is well, the second term is we've just finished. O of 1. And the first term is bounded by, is exactly, as we said, the excess over log. No, sorry, the excess multiplied by log 1 over epsilon. So the excess is u squared over log, is 4 pi L norm of u over log, and minus 1, and the L norm of v is 4 pi is 4 pi over is 4 pi log. And so anyway, this is true plus some error terms, plus O of 1. And so so typically the excess is log 1 over epsilon to the minus 1. And so the whole thing then is order 1. Okay, easy. And then finally, the last one is the most interesting one. Okay, so these are all matrix quantities, but it doesn't matter. So yeah, there's a phi ij and a ux, a phi ij and a vi and a u minus vj. But we're just going to do crude estimates here, and so we don't need to worry about that. So this will be bounded by phi infinity, and let's say u epsilon minus v epsilon L p and v epsilon L q, and let's take so as usual, 1 over p plus 1 over q is equal to 1. Okay, and so we already have estimate for L for v epsilon. From what we said before, and that will be up to a constant epsilon to the 2 over q minus 1. Where am I here? Okay, so that's what we have. And what about U minus V? So for this, here's what I would like to do, and I can't quite do it. But, well, okay, how should we say this? So what I know what U minus V is, well, I already have controlled the L2 norm. I know that the L2 norm is bounded. Let's see, this is divergent. This is blowing up as 2 over Q minus 1 is negative, because Q is greater than 2. So I need some decay for the other piece. I have bounds in L2, but all I know is it's bounded in L2. I don't know the decay. Okay, but I still know that, well, I still know that the flat norm of U minus V, of the curl of U minus V is small. So what can I get out of that? So, so here's what I'll do. So we have okay, so here's what I'd like. I'd like to say, so I can't do this, but I can do, but in fact, I can, what I'm going to say is wrong, but we can fix it. I'd like to say U epsilon minus V epsilon LP, let me first interpolate. U epsilon minus V epsilon L1 to the theta, and the same L2 to the 1 minus theta. And so then I want 1 over P is theta over 1 plus 1 minus theta over 2. And if we work this out, this says that 1 over P is 1/2 plus theta over 2. And so theta is 2 over P minus 1, which in terms of Q, I believe is going to be 2 times 1 minus 1 over Q minus 1, which is 1 minus 2 over Q. Okay, so it's the same exponent up here, but with the opposite sign. Okay, so let me see. And so, okay, and so let's continue. This is U epsilon minus V epsilon L1 to the 1 minus 2 over Q times a constant, because the L2 norm is bounded by a constant, and we raise to power, it's still bounded by a constant. Okay, and so if this L1 norm were of order epsilon, I would be in business. Then I would have an epsilon to the 1 minus 2 over Q times 2 over Q minus 1. The decay from the LP term would exactly balance the blowing up part from the LQ norm of V and IB, and the whole right-hand side would be order 1. And remember, that's all I need. So I'd like that. And is that true? So is the U epsilon minus V epsilon is this true? Well, here's what we would hope. Well, I mean, the point is the well, we know the curl of U minus V is of order epsilon in this funny homogeneous flat norm, and the homogeneous flat norm is almost the same as having -1. It's like a W minus in terms of scaling. It's like a W minus 1 comma 1 norm. It's like having -1 derivative in L1. And so having -1 derivative of order L1, of order epsilon, in L1 is like having 0 derivatives of order epsilon and, sorry, having -1 derivative of the curl. If I differentiate once, I take the curl, and that thing has -1 derivative of the L1 order of the -1 derivatives of order epsilon. That's like saying that the L1 norm of the original thing was order epsilon. That's what we hope, but it's not true. So probably not. But so here's what we know. The claim is that a weaker norm is indeed bounded. So the claim is okay. I'm sorry, I'm not give all the details. I'm going to mention stuff you may not know about, and if there's time later, I can fill in. But I claim that there's a Lorentz space norm, U epsilon minus V epsilon L1 infinity is bounded by constant times. So this is a weaker norm than L1. Well, this isn't true for U minus V in general. So for any let's say W L1 infinity in R3 is bounded by the curl of W in the homogeneous flat norm. Okay, let's write down the definition where W L1 infinity is the what is it? Is the supremum of it's a bound for the okay, I don't know what this stuff is. So what's the point? I look at the measure of the set of X. Where W of X is bigger than lambda. I look at that set. I look at this measure, and I divide by lambda, and I get the supreme over lambda positive. And so if I have an L1 function, then the set of, if the L1 norm is bounded by K, then by Chebyshev's inequality, the measure of the set of points where that function is bigger than lambda is at most K over lambda. Okay, and so if a function is in L1, it certainly has the property that this ratio is bounded. But one can easily write down functions like, say, in R3, the function 1 over x cubed will belong to the space L1 infinity, but will not belong to L1. And in particular, the kinds of vorticities we consider decay exactly like the velocity fields decay exactly like x cubed. And so these will fail to be in L1. The decay is too slow to be in L1, but they will be in this Lorentz space L1 infinity. I don't know what's wrong with this, what this stuff is about. Okay, and so this this follows from sort of, well, so there are two claims. One is that we have this Lorentz space estimate, and the other is that in fact this interpolation inequality up here is still true if I replace L1 by the weaker space L1 infinity. Okay, and so we're using a little bit of harmonic analysis here, and the point is that often for interpolation inequalities, you can if I iterate between two spaces to get estimates. In fact, you can weaken the norm on the endpoints, and the thing will still be true. That's easy. That's the proof is short. Okay, and so then the argument is this is the argument that I replace this by L1 infinity, and then I use this claim, and then so combining these. Combining these, what happens? We complete the proof. Okay, and why is this true? Why is the claim true? So remember we proved that the homogeneous flat norm of W is the infimum of the L1 norm of nu. Okay, it can be a vector value measure, but we might as well regularize it a bit and make it a function such that the curl of nu is equal to W. Okay, so we prove that, and so so let's see, and so fix nu such that, well, the curl of nu is W, and the L1 norm of nu is less than 2 times the homogeneous flat norm of W. Then we have the curl of, sorry, I'm doing this all wrong as usual. Pardon my mistake. And so I'm interested in the everything I've said has been wrong for a while. No, this is right. So I'm interested in the homogeneous flat norm of the curl of W. Okay, and so here I want the curl of W, and I should have said if W is divergence free. If W is divergence free. And so remember, we're working with the Euler equation, everything is divergence free. The U is the Euler equation, it's divergence free. The V is by construction is divergence free. Okay, and so we have that the curl of nu is the curl of W. So the point is that the just recopying, and the divergence of W is 0, which is not true of the divergence of U. And so the point is that the W is the projection of nu onto the divergence free vector fields. Okay, if I project nu onto divergence free vector fields, then I'll get something who has the same curl and whose divergence is 0, and that will be W. Okay, and so so then I'm not going to write this down, but then we recall harmonic analysis. If you've seen this, you know. If you've seen this before, you know what I'm going to say, and if you don't, it'll be too. There's not time to go into it, but this operator is a classic operator in harmonic analysis, the one that takes a that projects a a vector field onto its divergence-free part. And so this Cauldron sigma, or this it's a singular integral operator. It's a singular integral operator. And so it actually is bounded from LP to LP for P strictly between 1 and infinity. And and as usual in harmonic analysis, at the endpoints it fails. And so in particular for this projection, which maps V onto W, is bounded from L1 into the weaker space L1 infinity. Okay, and so so harmonic analysis says that W L1 infinity, this is some kind of projection onto divergence-free things of V in L1 infinity, and this is bounded by a constant times the L1 norm of V. Okay, of nu, excuse me. And the L1 norm of nu in turn is bounded by the flat norm of W. Or the curl of W. I'm not getting this wrong. Okay, and so the moral is just that this norm, this flat norm that we introduced because it has a natural geometric meaning, a sort of natural geometric merged point of view, also interacts well with harmonic analysis estimates that one uses more typically in a PDE or order equation setting. And so by combining this, by combining these ingredients, we can carry out the program sketched above. We can say that we replace this by L1 infinity, we use the lemma, this will be, then we exactly get epsilon to the 1 minus 2 over q times epsilon to 2 over q minus 1. And so then we can conclude this. Okay, and so that's the proof of this theorem, of the first theorem, theorem 1. And again, we just appeal to some harmonic analysis stuff, but it's interesting that this geometric norm, this norm who's natural in the geometric setting, is also very convenient for applying the Cauldron sigma estimates to these singular integral these four integral estimates. Okay, and then quickly the second theorem is this one. So it says. Again, we've seen it before. I have a smooth flow, gamma. I assume four derivatives are bounded. I assume that it has a nice security radius around it. I have assertion of order equations. I don't care if it's smooth, but I assume that it remains that. Okay, I can assume what I want with initial data. That's nothing wrong with that. I assume that at time 0 it's concentrated around gamma naught, and I assume that its excess is small. So it has only enough, its L2 norm is basically only enough that's required to create the this initial vorticity, this initially concentrated vorticity, plus maybe order 1 or something. Okay, and then further, I assume that there's a curve lambda of t whose length is invariant, and its geometry is controlled. That's what this tells us, and finally, I assume that the vorticity always remains concentrated around it on an epsilon scale around this evolving curve. The conclusion is then the curve lambda, parameterizing the rough curve, is close to the curve gamma, parameterizing the binomial curve flow. Okay, there may be some shift there. We can't really control where the parameterizations start and end, but after you shift, the parameterizations there are close. Okay, and we'll do this quickly. But and unfortunately, I've changed the notation again. This is terrible. So, but this is what I called, say, X, capital X before. So remember, in the Weak-Strong uniqueness proof, we built this magical vector field out of the smooth solution little gamma of the binomial curvature flow. It had these remarkable properties. And so let's just write, okay, let's call it X everywhere. Okay, and so I define I define the E sub little gamma of lambda to be the sort of, it's the same thing that appeared in the weak-strong uniqueness proof. So it's the sort of excess of the rough curve lambda with respect to the smooth curve gamma. And it's measured by taking this vector field, built out of the smooth curve gamma, and integrating it over the rough curve lambda. And we saw that this measures a kind of a geometric H1 norm of the rough curve with respect to the smooth curve. Okay, so that's one thing. And then I can also do something very similar. So the idea here is I'm just going to pretend I have this vorticity who solves the Euler equation, and I'm going to just pretend that it's a weak solution with errors of the binomial curvature flow. And so if that were true, I'm just going to take the vorticity from that Euler solution, omega epsilon, and I'm going to, you know, essentially insert it into this excess function, which is supposed to measure how far it is from the smooth curve. So in other words, so above I was integrating, I had the same magic vector field. Well, here it is again. X. I had this magical vector field, and I integrated against the, I integrated over the rough curve. Here I'm just taking the dot product with the vorticity and integrating. But vorticity is by assumption concentrated near the rough curve. And so, so these things will be about equal, as we'll see in a second. So by assumption, indeed, you know, if I look at the difference between E sub gamma of lambda and E sub gamma of the vorticity omega, well, these are small because these involve integrating this. I should fix this. Integrating this vector field x against omega minus the vorticity interval minus the interval of the curve, and by assumption that's small when it acts on test functions whose gradient of curl is controlled, and so it's lower epsilon. Okay, so we have that, and then let's do the following. I will just show you the slides rather than writing because we're running out of time. Okay, and so so here the first line is the vorticity formulation of the Euler equation, right? If I differentiate this, one is a constant, so I'm just differentiating the Euler vorticity against some test function, and I know how that behaves. I know what d dt of omega is. It's the curl of the gradient, or sorry, the curl of the divergence of u tensor u. I know how to get this. So this is Euler. And again, I've tacitly rescaled time in a certain way. I've rescaled time to make this factor of 4 pi over log epsilon appear in the Euler equations in this on the right hand side of this first identity. Okay, but then the theorem we've just finished discussing, theorem 1, tells us that if, as we've assumed that the vorticity is concentrated around the curve lambda, and we've assumed that the excess is not too big, and so when that holds, the integral of iterating against this tensor involving the vorticity tensor with itself, that's basically like projecting onto the okay, sometimes I have identity minus tau tensor tau here, I have tau tensor, but it's basically like projecting onto the, see, projection onto the normal and the tangent are the same up to a sine because because this gradient of the curl is trace free. Anyway, so this is theorem 1. That integrating against, you can use like integrating against a tangent tensor tangent, the tangent to the rough curve lambda around which the vorticity is concentrated, the potentially rough curve, and then we get some errors. Okay, and then this is the these are the, say, magic properties. Of this curve x sub gamma. So remember, in the weak strong stability proof, we had exactly this an expression of this sort, and we said this was pointwise bounded. We don't need to know where we're evaluating this integrand, or we don't need to know what direction this unit vector tau sub lambda is pointed in. This is always bounded pointwise by a constant times 1 minus 1 minus this vector field x dot tau. Okay, we always have that pointwise inequality, and when you and that's exactly the integrand in here. Okay, so this integrand is always pointwise bounded by a multiple of this integrand, and so the integral is and that's bounded, and that's what value is. And so the integral is bounded by a constant times e sub gamma up to errors. Okay, what can I do now? Very quickly. So, well, the geometric error is like the vorticity error. These are always close. What did I say? Epsilon? Yeah, epsilon. And this is like, and so what can I do? I can integrate the above. S plus the integral of the errors ds 0 to t, and okay, and see okay, and then once I have this, this is like knowing that if I were allowed to differentiate this would say that ddt of e sub gamma is bounded by a constant e sub gamma, which would tell me that e sub gamma can grow at most exponentially. That's Grundle's inequality. The same is true actually if we have this in integral form, if we have this estimate in integral form rather than differential form. And so then Grundle's inequality, some form of Grundle's inequality. Implies that E sub gamma lambda t is bounded by a constant times e to the k t times e sub gamma of lambda at 0, and then there are other errors. Okay, and then this in turn, the initial excess, what is it? Well, we can assume this is epsilon. I feel like it can be small. And so this is small. I think the whole thing, if you keep track of the errors, ends up being of order log epsilon inverse. And I've written the dependence on things more carefully in the statement there. Okay, and so then finally, we've, as we've said, so in this way we conclude that we get control over this quantity, which is a measure of the distance of the rough curve from the smooth curve. And the last step is to show that, in fact, if we know, so earlier we allowed the rough curve to be just some weird thing, variable. If in fact we know that the rough curve is a Lipschitz curve, is the image of some Lipschitz pattern around it, then this excess in fact controls this distance. So it gives you kind of pointless control over the distance of the curves. Okay, and so then putting these things together, we get this final conclusion, which says, as we said before, is very far from proving this conjecture, but it says that the only possible learning law of motion is the binormal curvature law. Okay, I've run over, so let me stick around for a little while and see if there are any questions. That's all I have to say for today. So, and again, in the remaining week, I think there's a couple of weeks left. I'll talk about the Gross-Spaghetti equation and point vortices in 2D, just so we have some discussion of Gross-Spaghetti. And that's it for now. Okay. So let's see. Okay, good. And while I'm waiting, let me put these notes in the chat. And once they're in the Dropbox, I should be able to do that. Here it is. Okay, so that's available now if you are interested, and I'll wait a little while if you want to download it. Okay. And so we use some simple harmonic, it's not from the very first course on harmonic analysis, but some very well-known facts from harmonic analysis. Right, so what were they? They were, well, this thing about the interpolation with the L1 and being able to replace. So the first thing I did, interpolating with controlling LP by L1 and L2 for P1 and 2, that's really just Holder's inequality. It's the simplest interpolation there is. And then the fact that one can replace L1 by L1 common infinity by this weaker norm is actually is also like a 3-line proof. And then the harder estimate is this one that allowed us to control is this one. Right here. That this projection operation is okay. It's not bounded from L1 to L1, but it's bounded from L1 to the slightly weaker space. And in terms of, you can write down what this is explicit in terms of harmonic analysis, in terms of Fourier transform. So if I take the Fourier transform of a vector field, it's divergence free if so the divergence, the Fourier transform of the divergence is the of the vector field v is c dot v hat, and so we want c dot v hat to be 0. That means that to attain that on the harmonic analysis side, I take the vector v hat and I project it onto the space of, I project it onto the vector fields who are nowhere pointing in the radial direction. So there's a pointwise projection on the Fourier side. And so for example, it's clear this is bounded from L2 to L2 because you've just taken the Fourier transform and made it smaller by throwing out a piece of it. And right, the boundedness from other LP spaces is not so obvious. And that's the kind of thing that these harmonic analysis results are good for. Okay. So and the Fourier multiplier, the multiplier that achieves this operation is just the operation that. So on the Fourier side, I take it's just the operation that exactly projects a vector. So at the point C, it'll project the vector onto the part of it that's orthogonal to C. So it's identity minus C tangent C. That thing. Sorry, minus the C tangent C over the norm of C squared. So I subtract off the projection of the unit vector tangent C. Okay, I'm sort of talking to give you guys a chance to formulate questions if you wish, but I don't see that happening. So, okay. Okay, so I'll maybe sign off pretty soon. So let's stop this. And then again, the plan is Monday to start talking about the gross Pitié equation in 2 dimensions. Okay, so hope to see you then.